Welcome back to a new Flownex webinar. The industry we will focus on today is HVAC and the application is contaminant tracking. Your hosts are myself, Marinus.
And myself, Willie. Welcome, everyone.
For those of you joining for the first time, the format is usually a structured webinar with questions at the end. Therefore, feel free to type questions under the question tab at any time, and all of these will then be answered right at the end. So what is Flownex? Well, Flownex solves the flow and heat transfer in subsystems and large interconnected systems, which includes steady-state and transient simulations. Flownex further contains industry-standard components such as pipes, ducting, and turbomachinery, which can be easily interlinked in the easy-to-use user interface. A large library of different fluids, gases, as well as their mixtures are also available, extending this applicability of the software across industry. And last but not least, Flownex is developed in an NQA1 and ISO 9001 environment, ensuring that the best standards of quality are met. So, Willie, specifically, what can Flownex offer engineers who are in the HVAC industry?
Yes, so Marinus, first and foremost, Flownex contains various ducting components which are derived from the ASHRAE duct fitting database. Flownex further contains fans and blowers where the design engineer is capable of adding their own fan or blower charts. Different types of heat exchangers are also available, allowing the engineer to use built-in heat transfer correlations or custom-defined heat transfer correlations. Nodes and containers are further available to capture volumes in transient, and finally, Flownex solves the equations for mass, momentum, and energy conservation simultaneously.
Thank you, Willie. Let's now elaborate more on the topic for today.
So, HVAC engineers are generally required to perform different tasks when designing an HVAC system. For example, in a healthcare environment where the flow distribution plays a significant role in the design, it is crucial to minimize the cascading flow from different infectious areas to more general areas like common spaces, corridors, or office spaces.
This brings us to contaminant tracing.
That is correct. We will like to show the tasks of investigating flow distribution at the hand of contaminants spreading in an HVAC system, here specifically a healthcare facility. Then test required design changes and investigate their effect.
So something you will be using in the Flownex demonstration later on are so-called trace elements in Flownex. So what are trace elements and how will one do contaminant tracing using them?
Well, Marinus, in Flownex, trace elements represent particles or constituents that are being transported with a fluid, generally in low concentration, thus not affecting the fluid properties. Homogeneous mixing also occurs in fluid volumes, and the concentration can then be monitored along a specified network. Multiple trace elements can also be defined, and the buildup of concentrations can be easily identified. The engineer can also add or remove specified trace elements, which allows the behavior of filters to be captured in Flownex. Lastly, Flownex solves a mass balance based on the concentration of the trace elements on each node in steady state and transient, ensuring that the correct behavior is captured.
Right, so here let's quickly discuss some of the possible use cases which will benefit from using these trace elements in Flownex. So the first is, of course, contaminant tracking, as Willie will show us in a few minutes. Similarly, tracking the spread of certain isotopes in nuclear safety and containment systems is another. And an interesting fact, Willie, did you know that Flownex was used as part of the design for the Chernobyl New Safe Containment or NCS structure?
You might have mentioned it once or twice, Marinus.
Nothing wrong in stating the facts. So next is dust buildup in pneumatic conveying or mining systems. Here you will find the buildup of fines which are then released periodically and can be tracked. Another build-up type application is in a desalination plant where element concentrations will slowly increase over time. Closed-loop cycles, such as evaporative cooling tower circuits, have water-hardening chemicals which can build up over time, and the time should be understood. Lastly, where concentrations are important for the correct system function, such as within reverse osmosis water purification systems. So those are the different applications. The benefit would be being able to investigate or evaluate the role of these trace elements and their behavior in the existing flow network. So back to the content of today. I will be handing Willie the reins shortly, where he will explain and demonstrate two different use cases. The first is how Flownex will benefit the HVAC engineer's workflow with required design changes to an existing system, specifically in healthcare. The second example is to investigate the effect of a filter and design it to achieve the required guidelines that were set in the design, again against the backdrop of a medical facility. Willie, could you kindly explain the first example so that we can get an idea as to where Flownex fits into the HVAC design process?
Yes, Marinus. So some of the critical design requirements that an HVAC engineer must attend to for a healthcare HVAC design is to restrict the movement of air between departments. This will largely prohibit the spread of bioaerosols and decrease infection rates. The indoor air quality together with temperature and humidity are also important factors. Finally, the sophistication of the design to minimize transmission, which involves the designation of different types of rooms with different pressure and flow requirements. An interesting fact is that airborne transmission accounts for approximately 10% of all nosocomial infections, that is, infections that originate in a hospital. If we look at the typical room designation in a healthcare environment, there three main categories exist. The first are Class P, which are operating rooms and protective environments, for example. These rooms are usually kept at a positive pressure greater than 8 Pascal above atmosphere, and the optimal air change rate per hour is more than 12. The second being general rooms, which are kept at neutral and a required air change rate of 8. The third is Class N, which are typically isolation areas, and infection wards, which are kept under a negative pressure less than minus 2.5 pascals to atmosphere, with an air change rate of 12. These are typically set out parameters and of course might differ depending on the requirements of the healthcare industry.
And we'll be checking those pressures in the live example.
Definitely, Marinus. So for example, we will look at a mock-up example of a healthcare facility layout with the three types of rooms. Initially, we will solve the network to obtain a current flow distribution and also view the results for the trace element specification.
This being the existing system, what is then the requirement that has now led to the need for contaminant tracing?
Well, Marinus, due to the demand, the general wards needs to be converted to Class N or infection wards, as can be seen on the screen. And we need to ensure that the correct flow distribution is obtained so as to not increase the spread of bioaerosols from these wards. A change in HVAC design will be required to satisfy the new requirements, which is that these rooms of minimal cascade flow and also be kept at negative pressures. And lastly, we will investigate the new flow configuration. So looking at the current system layout, we have incoming flow from a supply fan to the two offices as well as the operating room. Furthermore, there are in and outflows between the rooms and also from the rooms to the common area as shown here. These flows are largely due to gaps between the doors and the opening and closing of the doors. Lastly, we have an exhaust fan drawing air from the system at the end of the healthcare facility, creating negative pressures in the infection wards.
This is an interesting representation of the flow configuration in a typical healthcare facility, but how would one then go about to model this in Flownex?
Yes, so in Flownex, we added the layout as a background image for reference, as you can see here. We then added volumes or reservoirs to represent the volumes of the rooms, as shown here. Ducting components are then placed between the rooms to model the pressure drop due to the flow. The pressure drop between the rooms and the common area is modeled with a damper type component. The fan is also modeled and a cooler is modeled with an obstruction and heatsink on the left top side here. Dampers are again used to model the pressure drop as the flow of air enters the room. Finally, an exhaust fan is also used to model the flow leaving the facility. So, let us jump to Flownex. This is the Flownex canvas and the Flownex simulation environment. So the first step that we need to do is first we want to define our trace elements, because if I zoom into the network a little bit, we want to create a contaminant tracing elements in this infection ward. So first of all, I'll go to charts and lookup tables. Under materials and fluids, I'll go to trace elements and I'll specify add category. I'll rename this category to, for example, webinar. And under here, I'll add two types of trace elements. The first one will be our bioaerosols. And the second one is dust. We'll just call this dust particles, which we will use in the webinar a little bit later. Now what we can do is we can edit the first trace element. We can now define the different trace elements that needs to be tracked. In this case, we'll use 3 contaminants. And we can press OK. The reason why we use 3 is, well, I'll show at the later stadium, is that we want to track the origin of each contaminant, even though the contaminant can be any type of bioaerosols that the engineer can define in Flownex. So the next step would be to activate the solving capabilities of these trace elements. For this, we go to solvers, flow solver, and under fluids, we want to specify solve trace elements as yes. What we can do now is we need to define the trace elements in our network. So we can specify or select any component, and we can ensure that the correct trace element is selected. Following this is we need to define where these trace elements originate. So in this case, our trace elements, which is the contaminants, and in this case, contaminant 1, we want it to originate in the infection ward. So we go to our node or our volume or reservoir, in this case, in our infection ward, and we can specify a direct mass addition of trace elements. In this case, we specify a trace element addition flow rate. In this case, it's a weighting factor of 1, and we specify the trace elements. For this contaminant 1, we want to specify it, say, for example, 1000 parts per million. We go to our second reservoir, and we do the same. And what we can do now is we can solve the network. So Marinus, I've already defined some result layers in this case. And in this case, I want to show the contaminant 1 in our network. So,
okay, so that color is representing the concentration of the trace elements at the specific locations, right?
That is exactly correct. And as you can see that the concentration is currently shown in our color scale over here. And what we can do is we can also look into each component. So for example, if I want to look into this component, I can see the exact amount of trace element concentration for contaminant 1. Now, interesting fact here is that you can definitely see that there's a color difference between these two reservoirs, and the reason being is that the flow rate through this reservoir is a little bit higher due to the flow distribution than in this reservoir. So Marinus, back to our workflow. In this case, we want to convert these two general wards into infection wards. So moving to our new design. As you can see in the backdrop here is I've converted the general wards into the infection wards as shown. So our first step now would be to add some contaminants to each of these infection wards. First of all, I'll click on infection ward 1 and I'll specify direct mass addition of trace elements. I'll specify contaminant 1 to say 1000 parts per million. I'll go to infection ward 2 and I'll do the same, but for contaminant 2. Furthermore, I'll go to infection ward 3 and I'll do the same for both of these reservoirs. And now I can continue to solve the network. So Marinus, let's look at the results. We go to result layers. Let's see how contaminant 1 spread through the network. As we can see, first and foremost, that these two infection wards already fails the design requirements because they are at a positive pressure. Furthermore, we can see that contaminant 1, where red highlights a high concentration, spreads through to our common area and as well to our infection ward 2 and infection ward 3. Now, in terms of HVAC design for hospital, this is not good. So what we want to do is we want to add exhaust vents to each of these infection wards. So to do this, I'll just activate our grid and we can go to components. We can specify ducting components, zoom in a little bit, and we can add an exhaust in our infection ward. For this, we'll use a damper component, connect it as shown, and another damper component, and connect it to our second infection ward. Now we'll make use of an elbow, connect it as shown, and a duct. Furthermore, we will also include a duct in this area and connect the components as shown. Furthermore, I'll also include an elbow over here and connect it as shown. So the next step is to define the geometry of each of these components. So I can for now multi-select some of these components and specify a width of 0.75 meters and a height of 0.5 meters. I can go to the components individually. I can specify an angle, say for example on the dampers in this case, and I can specify an angle of say 5 degrees. I can go to the elbow, let me multi-select the elbows, and I can specify an angle of about 90 degrees. Finally, I need to specify the length on each of these ducts, and let me specify 3 meters on each. What we can do now is we can zoom out a little bit. We can deactivate our grid, and we can solve the network. First of all, we can see that there's been a slight change in pressures and also that the distribution of the contaminants is slightly different. But there are still some cascading flow into our common areas and infection wards. So what we need to do now is we need to isolate our infection wards. To do this, I'll just close the dampers on each of the inlets as shown. Let me make the angle around 60 degrees. If I solve the network, we will see how the results update. So, Marinus, there we can see that the infection wards already show a great improvement in terms of its pressures being negative. And also if we look at contaminant 1, it now only cascades to our infection ward number 2, but then flows out through our system as shown. If we take a look at contaminant 2, we can see a very different story where contaminant 2 only stays in infection ward 2 and flows out through the system. And then again, looking at contaminant 3, it is contained in this infection ward. So this enables us to sort of quickly do design changes to our network and then immediately see the results on the canvas and see if we might need to adjust. For example, in this case, we needed to adjust the inlet flows to both of these infection wards in order to isolate the wards. So moving back to our presentation.
Wonderful. Thanks, Willie, for the first example. That was quite insightful and definitely a quick way to investigate design changes. This then concludes our first example. Now moving on to the second example of using a filter in the network. Willie, can we apply a filter to the trace elements? The goal being to investigate the effectiveness of the filter and then to make necessary design choices.
Yes, Marinus. So in Flownex, a filter can be modeled by removing some of the trace elements and adding a pressure drop. This functionality specifically allows the engineer to quickly determine the required filter ratio and for the flow requirements. In Flownex, we will make use of the obstruction component.
So this is part of the ducting library, correct?
That is correct. This component contains inputs, first of all, for its geometry and also screen dimensions, and further, the user is able to specify the filter ratio for the trace elements used. Jumping to Flownex, we will quickly show how this functionality can be modeled. So here we have our filtration network, and first and foremost, we will need to define our trace elements. In this case, we will be using dust particles. Going under materials and fluids again, trace elements, webinar, and we can see that we've already defined our dust particles as previously shown. We can now zoom into the network a bit, make sure that the correct trace elements are selected, and in this case it is correct as dust particles. Furthermore, we want to specify the amount of dust particles coming into our network, and we can just say specify trace elements. In this case, it's already selected as yes, and the amount of dust particles that's entering the network is set at 200. We can now solve the network. Also in our file explorer, we also want to disable the other network so that solving will be a little bit quicker. So let's look at the results. Looking at the results, we can see that the dust particles have distributed throughout our network quite significantly. And in this case, there are a lot of dust particles flowing into our operating room. So what we can do is we can include a filter at the inlet of the operating room's HVAC system. To do this, we'll go to Components and we'll add an obstruction. Zoom into the network a bit and connect it as shown. Finally, we need to define the dimensions of our screen. Go to the inputs, specify the width of 0.5 meters, the height of 0.5 meters, the area ratio and the pre-area ratio, defining the screen's dimensions. Make sure that the correct trace elements are selected. Furthermore, we also want to define the filter ratio. In this case, let's define it as 0.8 or 80%, and we can solve the network. So if we zoom out a bit, we can already see that the results are updated. In this case, the operating room is seeing a lot less dust in comparison to the common and office area. And of course, there's flow cascading from our operating room to our general ward. So it sees roughly the same amount of dust particles. So what we want to do is we wanted to design that the amount of dust particles is about 75 parts per million in our operating room. To do this, we can simply say designer setup. And this window pops up. We can simply say add, call it filter ratio, the equality constraints is our variable that we want to obtain. So we can drag and drop it. We can specify 75 parts per million. Also, we need to define the independent variables, go to our filter, and we want to change our dust filter ratio to obtain 75 parts per million of dust in our operating room. Let's say it must change it between 0.7 and 0.9. Close the window, and now we can simply run the designer. So what will happen is that our dust filter ratio will start changing until we have met our required 75 parts per million. To see the convergence, we can go to our console, and we can see that the convergence is lowering. Also, if we click on our reservoir component, we can see that the dust particles, it's getting closer and closer to our solution. If we click on our obstruction component, we can see that the filter ratio is also changing. Now, Marinus, this is a very handy feature, as the engineer can quickly make changes or design changes, and Flownex will obtain a solution for the requirements. We'll just wait for the convergence to settle. And there, the designer found a solution. So, currently at a filter rate of 0.84, click on our reservoir, we can see the dust particles settled at 75 parts per million. So, jumping back to our presentation.
That was great, Willie. Thank you very much for taking us through the different capabilities. I'll just quickly summarize what we looked at today. We looked at how Flownex can be a valuable modeling tool for HVAC engineers in this specific type of system. The available components and fluid models could also then be used for other industrial or medical systems where flow and heat transfer are involved. Special behaviors such as modeling the flow distribution through a healthcare facility and quickly displaying the most important results in a visual manner. Furthermore, that Flownex is easy to use, making design choices quickly and effortlessly, thereby saving time and money for the design engineer. So Willie, how can we take this further? Are there any other design tasks where Flownex can prove to be even more valuable?
Well, Marinus, for most components in Flownex, they contain inputs that are widely accepted in industry. This gives the design engineer the capability to easily determine sizing and parameters for components such as valves, fans, or any other type of ventilation or mechanical components during the detailed design phase. Also, off-the-shelf HVAC components can be modeled and evaluated whether they will perform according to the design specifications, and the performance evaluated against set industry standards. And by using trace elements, various studies can be performed to ensure that a design can meet its requirements.
Okay, that concludes our presentation for today. Willie, many thanks for the excellent demonstrations.
It was my pleasure, Marinus. I really hope that the viewers enjoyed it as much as I did.
If you have any further inquiries, please feel free to visit our website or send us an email to the address as shown on your screen. We will then be happy to get in touch with you. For our live audience, we shall now proceed to answer any of the questions that were posted by you on the questions tab. So you may also ask any other questions that you might still have, and our team will answer these through the platform. Thank you.